Hello and welcome to the final lecture session in the 3D graphics programming module, which is entitled 3D rendering is a lie. Oh, and you are only now telling us. Well, better late than never. So, the full title of the session is 3D rendering is a lie or beyond rasterization methods and local lighting. So, what's wrong with rasterization and what we've been doing about it so far? It's the first topic in the agenda. Then we will very briefly talk about physically based rendering, PBR, very briefly, because this topic was already discussed in one of the past sessions on the 18th of March. Unity shader graphs and game engines. And then we will look into a range of techniques known in 3D graphics as Global Illumination. And this will include stuff like Ambient Occlusion, Radiosity, Ray Tracing, which is very trendy now, and even some techniques beyond Ray Tracing like Path Tracing and Photon Mapping. The last part of this lecture session is about RTX, what is it, and how to use it. Rasterization. Rasterization is basically everything we've been doing so far in this module. It's incredibly efficient and it can provide a high level of realism. So it is still kind of a standard 3D graphics method, but it is also so-called a local method. So shading of a fragment, yes, a fragment like in fragment shader. Shading of a fragment depends on its position, the light position, so lighting, and the camera position. Nothing else. And in this lecture, we will see that there is a lot of other stuff, of other conditions that can affect the shading or lighting or rendering of a fragment. So far we did transparency, or if you prefer translucency, through an alpha channel and object ordering, reflections through environment maps or planar reflections through other kind of tricks, shadows through shadow maps, diffused ambient light through actually we didn't do that. Okay, so basically with local methods we use a set of methods, analog methods, that may work or may not work in a given context. Basically, 3D graphics is a collection of cheating methods, okay, for every situation, for every special effect, we have some kind of a method. This is what I meant when I told local methods are a lie. The first method that we could approach in order to make our rendering process more consistent and more physically based actually is something that is known as physically based shading. And this topic was discussed in quite detailedly in shader graphs lecture. It was unit 3.02. So I will just give you a very quick, very brief resume of what physically based shading is. So first of all, this is the current trend in rendering, possible thanks to recent development in graphics hardware. It provides better simulation of physically realistic material-light interaction. The goal is to have more accurate rendering, and first of all, more accurately model flow of light. And a good example of physically based shading is so-called standard shaders used in Unity. In my lecture about shader graphs, I gave you a few hints about how you could possibly physically enhance your local methods of rendering, so what we did in this module. So please, if you haven't watched that lecture yet, ensure that you watched it as well. Alright, so what is physically based shading? The official definition is here: user-friendly way of achieving a consistent, that's the keyword here, plausible look under different lighting conditions. It models how light behaves in reality without using multiple ad hoc models that may or may not work. A very good introduction you can find in this paper by Jeff Russell, Basic Theory of Physically Based Rendering. You can find the link here, or it is also published in Canvas, but not in this unit, in Unit 302 about shader graphs. Just one more thing, this image here, which was initially used by Unity to market their then new standard shader based on PBS, physically based shading, everything in this picture uses just a single standard shader, so the technique is quite powerful. In that lecture, we discussed in more detail some main principles of physically based shading. One of them was, for example, energy conservation. Basically, because the energy radiated by a surface must be equal to, or at least not bigger than, not larger than, not greater than the amount of energy previously absorbed by this surface. So basically, surfaces absorb light energy and then radiate, and this radiation is what we can see. This is the quantum actually based theory of how really reflections or diffusion of light works. Okay, basically, according to this theory, if you have a surface that uses some of this absorbed light energy to create reflections, to increase the reflectivity, and for example create this bright, quite large spots of specular light, then the general diffuse color called albedo, the diffuse color of the diffused light, will be darker. So with increasing reflectivity, the background, the reflective color becomes darker. Another aspect of physically based shading are Fresnel reflections. Basically a simple theorem saying that every material will be most reflective at the place in which it is glancing from the view, so at the edge of this marble rather than the center. Whatever kind of material it is, rubber is basically not very reflective, but even rubber will be quite reflective near the edge, and even something that is quite reflective will be less reflective in the center, more reflective at the edge. So this is an example of Fresnel reflections. So this is one of the methods you can apply in order to come a bit closer to physically realistic rendering. But even PBS or PBR, there are two acronyms. PBS stands for physically based shading, PBR stands for physically based rendering, basically the same thing. So physically based rendering / shading is still what we call a local method. Okay. What I mean is a local method is in opposition to something that we call global illumination. This is basically the difference between left image and the right image. The left image only uses local local methods, and well, it looks quite well. We have reflections, refractions, no, it's a reflection basically, and quite interesting lighting, so it's not looking bad. But so this scene is quite characteristic because it has two walls with very clear coloring. There is a red wall on the left side and the green wall, which is not actually directly seen, but you can see the green wall in this reflection here. So the green wall is on somewhere on the right. With global illumination, we will see the shading created by the light diffused or reflected from these two walls, and we will get this slightly reddish shading here and quite deeply greenish here. It's deeper here than here because this red shading is next to the source of the light. Okay, so in the darker corners, this reflected light will be more visible. So basically, global illumination is a group of algorithms that take into account not only the light coming directly from the source, so-called direct illumination, but also light reflected by other surfaces in the scene, which may be reflective or not. Okay, so we take into consideration reflections, refractions, and shadows. So once again, a view of this scene. The simple approach to global illumination is known as ambient occlusion. It's not necessarily physically correct, but gives good results in general, and it's perfect for pre-computation. So if you pre-compute this ambient occlusion, often using the simple ray casting method to calculate how exposed is a point to outer surfaces. Ambient occlusion will not calculate the colored shades like in the previous illustration, but it will find out the parts of the scene which are typically in deeper shadows because they are in the corners or something like that. As I mentioned, often used method is ray casting. Don't confuse ray casting with ray tracing. This is a relatively simple algorithm used in the once famous game Wolfenstein 3D. This was one of the first ever created three-dimensional games, which quite a funny style of graphics. Basically, ray casting is scanning the 3D surface in order to find the closest surface to the given surface. And if you discover this surface in close proximity, you can assume that this part of the surface will typically be darker because of shading. Real-world example of ambient occlusion, the left-hand side image only shows the result of ambient occlusion. So there is no direct light. Direct light is in the middle picture. Ambient occlusion just analyzes the relative position between various surfaces, and quite an amazing thing about ambient occlusion is that ambient occlusion, AO, in popularly abbreviated to AO, AO can be very easily baked into textures, and quite often when you look through collections of textures, you will find albedo or color texture, normal texture, height texture, specular texture, and one of them is occlusion or AO texture. This texture looks like this. And now, with a typical, entirely local rendering with just direct light, you can have a rendering like this, but if you combine it with ambient occlusion, you get quite better quality. You can get something like this, and these shadows here wouldn't be available without ambient occlusion, with just direct light. You might want to recreate them with shadow maps, but of course shadow maps are costly, and the application of pre-baked ambient occlusion is very easy technically and very fast computationally. Another technique of global illumination, still simplified but a little bit more advanced, is known as SSAO, Screen Space Ambient Occlusion, used for the first time in Crisis by Crytek quite a long time ago. This technique uses the depth buffer rendered to a texture to determine ambient lighting. The difference between using SSAO and not using is in the picture. This scene, I think, is from Half-Life 2 game. On the left we have without SSAO, and on the right we have these slight shadows visible here and here. This provides a lot of depth to this scene, actually. Another technique which is quite advanced, and it is also quite computationally complex, is called Radiosity. Radiosity considers paths of light that are reflected diffusely from some other surfaces some number of times. The same scene with indirect illumination looks like on the left. With Radiosity it looks like on the right. So you can see very nicely the shadows are quite soft, and also we have other aspects of lighting. For example, in front of these windows, the floor becomes very bright. So these are effects that are not easily possible with direct illumination. Radiosity is an iterative method. So here you have comparison between first, second, third, and 16th pass of calculation. Each pass is connected to one more number of times when the light can be reflected from other surfaces. So basically every surface in this scene becomes, in a way, becomes the source of the light. Okay. Like in real world, each surface absorbs light but also partially reflects this light back. This example shows 79th iteration of a radiosity-based scene implemented in OpenGL. The method only involves diffuse reflections, therefore it is unaffected by the position of the observer. So even though radiosity is incredibly time-consuming, it is also quite good for pre-computation or baking. So you can create fantastic scenes which are relatively cheap in terms of real-time rendering. And now we are arriving to the queen of all rendering methods, or the king, ray tracing. Ray tracing, it's tracing the path of light backwards from the image pixel back to the source of the light. Unlike Radiosity, it will render stuff like things like reflections, refractions, or translucency, so playing, interacting, the light interacting with transparent or semi-transparent objects. It will automatically create shadows, it will automatically create depth of field, and many more. A very high degree of visual realism, but also very high computational cost. Two examples of ray traced scenes are here in front of you. This looks amazing, and how it can be produced. It's a totally different rendering method from what we would normally do. First of all, ray tracing requires a mathematical model of the scene geometry, which is then used to backtrack the light rays. And at the end of the day, you will use Lambert or Phong method to calculate the final color value. But first of all, here we have a scene which contains two sources of light. L1 is here, L2 is here, and then a solid ellipse, a translucent sphere, okay, so semi-transparent, and a reflective box, that's C. The point O is the observer of this scene, and we can see the a part of visibility cone. To determine the value of any fragment, for example, somewhere here, we have to track back the ray of light. So, tracking back, we arrive here to the surface of the translucent sphere, where, quite interestingly, this ray will divide into reflected light, which we can follow all the way to the solid ellipse, and for this point on the surface of the ellipse, we will calculate right now, right at this moment, the Lambert or Phong based rendering value using these two light sources. And we also have refracted light which goes through, well, actually it came from the inside of this translucent sphere. We have refraction here, another reflection from the reflective box in here, and we could follow this ray even further, eventually finding what kind of a color value point it should get. So this is the technical rule behind ray tracing. If you like a method which is even more complex than ray tracing, here it is, path tracing. It uses Monte Carlo method, so random probing the surface to simulate many rays, which will be useful for radiating surfaces such as this emissive bulb or sphere in this picture here. Ray tracing is good basically for point lights, and if you have larger surfaces radiating light, path tracing may be even better. And one of the latest and most advanced techniques is known in 3D world as photon mapping. This method may use even millions simulated photons to render complex optical effects, not always accurately, but if you look at this picture on the right, and this shadow of this glass, it's absolutely incredible. This is also an iterative method, and it's quite time consuming. So now when we have reviewed most of most important global illumination methods, the last topic, and quite exciting topic actually, is RTX. What is RTX. RTX is hardware accelerated ray tracing. This method will require latest GPUs such as NVIDIA RTX or AMD Radeon RX. We don't currently have RTX GPUs in the games lab we used for the module, so SB1026. But we have a new lab in the top floor of Sopwith building, SB3034. This room is full of new computers with NVIDIA RTX A5000 graphics cards on board. And these computers can play ray tracing, the very advanced global illumination technique, in real time, interactive real time. For this, you would also need the latest versions of graphics frameworks, such as DirectX version 12 or Vulkan. Vulkan, if you remember, I hope you remember, Vulkan is the next version, next generation after OpenGL. Currently, OpenGL cannot support RTX hardware accelerated ray tracing. Is it going to be ever available in OpenGL? I don't know. The Kronos, the steering group over OpenGL, seems to navigate towards Vulkan as the successor of this technology, and OpenGL may remain in the current stage, so not supporting RTX. This is one example of a scene generated in real time using NVIDIA hardware and Remedy's no-flight game engine. RTX Basics, if there is anything basic here, it is here. RTX provides 5 new shader types, creating a new ray tracing pipeline. This is a programming model for a single ray, for an analysis of a single ray. So as you can see, these rays can be generated, intersections found, hits found. There is a decision between miss and closest hit. Miss means that the ray will be finalized because it just escapes beyond the scene. Basically, this structure allows for finding the surface, which is at the end of a complex ray, which can be refracted, like in the picture I showed you a few slides before. For this to work, we actually need a two-level hierarchy for geometry. So first of all, the GPU or the shader program must receive a representation of the full 3D environment in the mathematical format that is optimal for being traversed in the GPU. This uses something that is called a shader table. So as you can see, this hierarchy of 3D objects is traversed by the GPU, and eventually it is decided which fragment in which object should be rendered. But for this, we need a structure that is known as a shader table. This is a data structure that defines which shader is associated with which object in the scene. So rather than using a simple structure as we did in OpenGL, even when we created several shader programs, we always eventually called the use function on one of those programs to select which program we are using in the given moment. In the water rendering scene, we had a basic renderer. basic shader, sorry, terrain shader, water shader, and we just switched between them. Terrain shader, render terrain, water shader, render water. Most applications today simply batch draw calls using a single material shader pair at a time. But this approach wouldn't work in the ray tracing pipeline simply because the ray may end up in any object after this traversal through the acceleration structure. It may end up in any object of the scene geometry, and we know that this process can be quite complex with multiple reflections, multiple refractions, and even dividing a single ray into two rays, like in this case that I showed a few slides ago. So this ray will end up in any object of the scene geometry, and this is why the shader table must provide this information, which shader should be applied for the final surface rendered. Time to show some examples of RTX. And this is one of the famous RTX demos known as elevator demo, run live from one of our NVIDIA RTX 5000 computers.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector.
If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What?
You think she heard us? Yeah, I think she heard us.
At least we blend in for once.
Wow, that was pretty amazing, particularly if you consider all this was created in real time. There was no pre-recording. I mean, what you've seen was obviously pre-recorded, but I am right now sitting in front of one of our new RTX machines, and I have just experienced this entire scene rendered in true real time. In Canvas, you will find a few more examples of RTX technology in action, but I will stop at this point today. Thank you very much for watching, and goodbye.